Imagine standing alone in the darkness. Nothing seems unusual, just sand, rocks, dead leaves. But something is already there, less than 2 feet away. You don't see it. You don't hear it. Until suddenly, the darkness begins to make a sound. And by the time you realize what you're looking at, it's already too late to react. The sound is a dry, whispering hiss. This is Echis carinatus, the saw-scaled viper. Classified within the family Viperidae, it was first described in 1801. In South Asia, most individuals measure just 1 to 2 feet in length. While some geographic variation exists across its range, the typical adult remains exceptionally small. It is an animal that can easily fit within the palm of a human hand. Yet, this modest scale is entirely deceptive. This is the snake that shouldn't be this dangerous. Nothing about this snake is normal. It possesses a short, stout, heavily built body, terminating in a sharply triangular head that is noticeably broader than its neck. Its eyes feature vertical, elliptical pupils built for low-light survival. The skin is covered in strongly keeled scales with raised ridges. Across its back, a pattern of cryptic brown, gray, sandy, or reddish tones with darker patterning breaks up its outline. This design allows it to dissolve completely into dry earth, rocky terrain, or agricultural margins. To an unsuspecting traveler, the snake is nearly invisible. It is a highly venomous predator hidden in plain sight, relying on absolute concealment. At this size, it does not look like a lethal threat. That is exactly why it is so frequently underestimated. The dry plains, sandy riverbanks, are habitats of low visibility, defined by gravel, loose soil, and sparse scrub. At the boundaries of these arid zones, agricultural fields push directly into the wilderness, creating a vast network of edges where daily human labor overlaps with the natural world. This is where the encounter occurs. It is during the cooler hours of twilight or under the cover of night that this terrain becomes active. The viper shifts its behavior based on the season, sometimes moving during the crepuscular hours of late afternoon when temperatures drop, but most often waiting for absolute darkness to mask its presence. It does not wander aimlessly. It waits. Its movements are tied directly to the paths of small rodents, lizards, and other ground prey. Because its activity is dictated solely by the search for food, encounters with humans are entirely accidental, a simple byproduct of shared space. When a person approaches, the snake does not flee. It freezes. By pressing its body into the leaf litter and matching the precise texture of the dry stones, it breaks up its physical outline. In the dark, a person walking through the fields has virtually no chance of spotting it. It doesn't need to chase you, it only needs you to miss it. When visual detection becomes impossible, the boundary between safety and disaster is reduced to a single step. Yet, even in absolute darkness, the snake does not always remain a silent shadow. A different kind of warning begins to emerge from the gravel, a sound that challenges the quiet of the night. That dry, sizzling rasp is the product of an extraordinary physical friction. This behavior is called stridulation. Unlike other vipers, this snake lacks a segmented tail mechanism. Instead, it loops its body into a tight, fluid figure 8 and begins to move. As these loops slide past one another, specialized, serrated scales on its lateral flanks grate against each other. It is not a rattlesnake rattle. It is the sound of scales rubbing against scales. While the pitch and texture of this warning vary qualitatively with the snake's size and the dry air, the biological purpose remains constant. It is an economical defense, a low-energy acoustic boundary designed to avoid a costly physical confrontation. The viper is not hunting, it is holding its ground. But if the disturbance continues, the rhythm quickens. The loops slide faster, the saw-like hiss rising in volume. It is a rapid defensive threat response, a calculated escalation. When this acoustic warning fails to push the danger away, the restless, rubbing coils suddenly freeze, and the snake prepares to launch. The strike is a sudden, explosive release of compressed tension. From its tight defensive coil, the viper launches forward. Its raised head and tensed muscles act like a loaded spring, allowing the snake to maintain a nearly motionless defensive position until the split second of contact. Inside the mouth, a specialized venom delivery apparatus shifts with mechanical precision. The viper possesses hinged fangs that fold back against the roof of the mouth when unused. As the jaws gap open, these bones rotate, swinging the fangs forward into a vertical position. Secure ducts link the hollow fangs directly to the primary venom glands situated behind the eyes, ready to channel the fluid under pressure. This defensive response is extremely rapid, occurring faster than the human eye can track. Yet, this violence is strictly localized. The animal remains anchored to its position. Continued disturbance will trigger subsequent defensive strikes, but it will never result in pursuit. The snake does not need to pursue the threat. It only needs a single opening. The physical entry of the venom is often marked by immediate local pain, rapid swelling, and bruising around the puncture wounds. Yet, the true danger of this bite does not remain localized. It travels swiftly into the bloodstream and the circulatory system, targeting the very chemistry that keeps us alive. To understand how this occurs, one must look at how healthy blood behaves. In a healthy individual, a complex cascade of chemical signals operates continuously to maintain fluid balance. When a blood vessel is damaged, the body initiates a precise repair sequence. Special proteins called clotting factors, including a primary building block known as fibrinogen, are rapidly mobilized. These factors act as the physical materials needed to build and stabilize a secure mesh, sealing the breach and stopping the loss of blood. When this essential biological system fails, the resulting state is defined as coagulopathy, which is a complete failure of the body's normal clotting mechanisms. The venom can interfere with the system the body uses to stop itself from bleeding. Within the chemical cocktail of the viper's venom are broad classes of toxins, primarily metalloproteinases and serine proteases. These proteins do not act as simple blood thinners. Instead, they act as rogue activators. Once inside the bloodstream, they systematically disrupt the delicate regulatory pathways that control coagulation. They force the body's clotting factors to activate abnormally and all at once, sparking microscopic clots throughout the blood vessels. This hyperactivation rapidly consumes the body's entire reserve of fibrinogen and other vital proteins. With these resources completely depleted, the body loses its ability to control bleeding. This state of systemic depletion is called venom-induced consumption coagulopathy, or VICC. The clinical reality of VICC is deceptive. It is not simply a state of thin blood. A person who has been bitten might initially appear stable, showing minimal symptoms beyond mild local swelling. They might even believe the encounter was minor and require no attention. But beneath the surface, the biological machinery required to stop a hemorrhage is already gone. Over the following hours, as the toxins continue their work, the lack of clotting factors can lead to spontaneous, systemic bleeding. Gums may bleed, old wounds might reopen, and bruises can spread far from the site of the bite. Without intervention, this systemic hemorrhage can progress to life-threatening internal bleeding or severe kidney injury, as the kidneys struggle to process the cellular debris of this internal collapse. Because the depletion occurs over time, the patient's condition can worsen dramatically, after an initially reassuring assessment. This quiet, progressive failure of the blood's defensive system is what makes envenoming by this snake so exceptionally dangerous. Not every strike from a saw-scaled viper results in disaster. Some are dry bites, where no venom is injected at all. Even when venom is delivered, there is a vast clinical range between mild envenoming and a severe medical emergency. The ultimate outcome depends on several variables: the volume of venom injected, the bite's location, patient health, local geography, and the speed of medical intervention. When envenoming occurs, the care pathway begins with rapid immobilization of the limb and immediate transport to a clinic. Here, clinicians evaluate the patient using the 20-minute whole blood clotting test, or 20 WBCT. A sample of venous blood is held in a clean glass tube and observed for 20 minutes. If it fails to clot, systemic envenoming is confirmed. Laboratories can also run complementary checks, measuring prothrombin time, international normalized ratio, activated partial thromboplastin time, fibrinogen levels, and platelet counts. Because coagulopathy evolves dynamically, repeated monitoring is required. If the blood remains unclotted, antivenom is administered to neutralize the circulating toxins. But antivenom is not an instant cure. It cannot immediately reverse damage already done to blood vessels. If clotting abnormalities persist, clinicians must reassess and administer additional doses. For severe cases involving major bleeding or organ complications, advanced supportive care, including fresh frozen plasma, cryoprecipitate, and renal monitoring, is necessary under qualified medical supervision. Yet, this clinical ideal is often compromised. In remote areas, transport delays, local antivenom shortages, and limited laboratory capacity can drastically alter the outcome. This leaves doctors operating under extreme pressure and raises a basic question: can a single, national treatment framework ever truly account for the regional variations of this venom? To answer that, we must look at how India categorizes its medical threats. This national category, established in the mid to late 20th century, is known as the Big Four. It unites the Indian cobra, Naja naja, the common krait, Bungarus caeruleus, Russell's viper, Daboia russelli, saw-scaled viper, Echis carinatus. This grouping was never meant to suggest these snakes behave similarly. Rather, it serves as a practical medical and antivenom production system. The scale of the problem is massive. Globally, the World Health Organization estimates roughly 5.4 million snakebites occur each year, leading to between 1.8 and 2.7 million envenomings and 81,400, 10 to 137,880 deaths. In India alone, estimates suggest roughly 5 million bites and up to approximately 2.7 million envenomings annually, though rural underreporting, uneven hospital access, and differences in case recording obscure the exact numbers. These figures describe the scale of snakebite in India. They do not belong to one species. Contemporary surveillance continues to examine how fully a uniform category represents actual regional realities. In the arid expanse of western and northwestern India, across the plains of Gujarat, Rajasthan, Haryana, and Punjab, the saw-scaled viper takes the form of a distinct subspecies. First described in the mid-20th century, Echis carinatus sochereki introduces a complex scientific challenge to standard emergency medicine. What happens when venom changes from one population to another? Geographically separated populations can differ significantly in their toxin composition. Recent comparative proteomic work reveals distinct variations in the relative abundance of specific toxin families, including phospholipases, between these regional vipers. This molecular shift has direct consequences in local clinics. Doctors treating bites in Western India have documented selected cases of severe consumption coagulopathy and significant bleeding that do not easily resolve. In these patients, clotting abnormalities can remain concerningly high even after the administration of standard polyvalent antivenom. Because antibodies manufactured using venom primarily from southern populations may recognize the toxins of northern populations less efficiently, the clinical outcome depends on a delicate immunological fit. The question is not whether antivenom works. It is how closely the treatment matches the venom in front of it. These findings represent localized clinical observations and specific laboratory studies, not proof of widespread antivenom resistance. Standard polyvalent antivenom remains a critical, life-saving therapy when clinically indicated. Laboratory neutralization trials do not perfectly predict every clinical outcome, but they emphasize a fundamental scientific reality. Effective treatment relies on continuous representative venom sampling and precise regional surveillance. The survival of this viper relies on a perfectly linked chain of evolutionary choices. No single adaptation accounts for the danger it presents. Instead, each trait builds upon the last to form a seamless defensive system. It begins with a flawless concealment that completely defeats visual detection, allowing the snake to exist inches from danger without ever being noticed. It operates in the quiet hours of the night, moving through the terrain when human visibility is at its lowest. When a potential threat approaches, it produces a dry, scale-based warning that functions as an economical, pre-contact defense. If that warning is ignored, the animal deploys an incredibly rapid defensive strike. This physical response is backed by a highly potent venom that evolved primarily to subdue small desert prey, but doubles as a devastating weapon of self-preservation. Nothing about this snake is normal. These highly specialized biological solutions were never designed to target humans. They evolved over millions of years to keep a small, ground-dwelling predator alive in a harsh and competitive terrain. But because these survival strategies are so remarkably effective, they create a persistent hazard wherever the snake's natural territory overlaps with human activity. Where agricultural fields push into dry scrub, and where people walk dark paths, tend to livestock at night, or live near field margins, accidental encounters become inevitable. The snake is not acting out of malice or anger. It is not evil, vengeful, or deliberately aggressive. It simply reacts to perceived danger using the specific tools that nature provided. Coexistence with such an animal requires discarding ancient myths of aggression and replacing them with a practical, quiet respect. Real respect means avoiding unnecessary contact, maintaining continuous vigilance in shared environments, and treating every suspected encounter with absolute medical urgency. The ultimate hazard does not stem from a desire to attack, but from a simple human miscalculation. We constantly assume that a small, quiet creature cannot pose a lethal threat, and that assumption is precisely where the danger begins. In our minds, we associate great danger with great size, expecting a predator to be loud, imposing, and obvious. The snake challenges this very instinct, proving that the quietest designs are often the most effective. It doesn't need to be the biggest snake in the world. It doesn't need to chase you. It doesn't even need to be seen. It only needs to remain exactly what evolution made it: small, silent, and almost impossible to notice. It doesn't need to be the biggest snake in the world. It doesn't need to chase you. It doesn't even need to be seen. It only needs to remain exactly what evolution made it: Small, silent, and almost impossible.